Hello everyone, welcome back to my YouTube channel. I'm Keerthana currently pursuing my BA at Sri Venkateswara College of Engineering, Bangalore, from the Department of Computer Science and Engineering. Today I'll be discussing about the subject called Data Structures and Applications, particularly about the topic called Data Structure in Theoretical Approach. Before going to our main topic, now let us discuss about Table of Content. Introduction. Second, sequential search. Third, binary search. Fourth, binary search tree. Fifth, common internal solving algorithms. Sixth, conclusion. Introduction. Data structures serve as the basis for abstract data types. The ADT defines the logical form of the data type. The data structure implements the physical form of the data type. Different types of data structures are suited to different kinds of applications. Some are highly specialized to specific tasks. For example, relational database commonly use B-tree index for data retrieval, while compiler implementations usually use hash tables to look up identifiers. Data structures provide a means to manage large amounts of data efficiently for users such as large databases and Internet indexing services. Usually, efficient data structures are key to designing efficient algorithms. The implementation of data structure usually requires writing a set of procedures that create and manipulate instance of that structure. The efficiency of a data structure cannot be analyzed separately from those operations. This observation motivates the theoretical concept of abstract data type. A data structure that is defined indirectly by the operations that may be performed on it, and the mathematical properties of those operations, including their space and time cost. An array is a number of elements in a specific order, typically all of the same type. Depending on the language, individual elements may either be all forced to be some same data type or maybe from almost any type. Elements are accessed using the integer index to specify which element is required. Our next topic is sequential search. When data items are stored in a collection such as list, we say that they have a linear or sequential relationship. Each data item is stored in a position which is relative to the others. In Python list, these relative positions are the index values of the individual items. Since these index values are ordered, it is possible for us to visit them in sequence. The process gives rise to our first searching technique, the sequential search. Starting at the first item in the list, we simply move them to item, following the underlying sequential ordering until we either find what we are looking for or run out of items. If we run out of items, we have discovered that item we are searching was not present. Analysis of sequential search. Analysis of sequential search to analyze searching algorithms that we need to decide on a basic unit of computation. Recall that this is typically a common step that must be repeated in order to solve the problem. For searching, it makes sense to count the number of comparisons performed. Each comparison may or may not discover the item which we are looking for. In addition, we make another assumption here. The list is placed randomly into the list. In other words, the probability that the item we are looking for is another particular position is exactly at the same position of the list. Algorithm of sequential search is first we'll select goal and list size. If I is equal to 0, we'll use the while condition that if I is less than size and list of I which will be not equal to goal. If I is equals to I plus 1, then I will be our size. Otherwise, we'll return the I. Threaded binary tree. In a threaded binary tree, all the null pointers which wasted the space is linked in representation and converted into useful links called threads. Thus, representation of a binary tree using these thread is called threaded binary tree. In the case where the item is in the list, the analysis is not so straightforward. There, there are actually three different scenarios that can occur. In the best case, we'll find the item in the first place we look. At the beginning of the list, we'll need to only one comparison. In the worst case, we'll not discover the item until a last comparison or the nth comparison. Next topic is binary search. Binary search is a fast search algorithm with runtime complexity of O into log n. This search algorithm works on the principle of divide and conquer. For this algorithm to work properly, the data collection should be in the sorted form. Binary search looks for a particular item by comparing the middlemost item of the collection. If a match occurs, then the index of item is returned. If the middle item is greater than the item, then the item is searched in the subarray of left of the middle item. Otherwise, the item is searched in the subarray of right of the middle item. This process continues on the subarray as well until the size of subarray reduces to zero. B-trees are generalizations of binary search trees, in that they can have a variable number of subtrees at each node. While child nodes have predefined range, they will not necessarily be filled with data, meaning B-trees can potentially waste some space. The advantage is that B-trees do not need to be rebalanced as frequently as other self-balancing trees. Due to the variable range of their node length, B-trees are optimized for systems that read large blocks of data. They are also commonly used in databases. A ternary search tree is a type of tree that can have three nodes, a LO kid, a equal kid, and a HI kid. Each node stores a single character and tree itself. It ordered the same way a binary search tree is, with the exception of a possible third node. Searching a ternary search tree involves passing in a string to test whether any path contains it. The time complexity of searching and balancing ternary tree is O into log n. It is observed that BST worst case performance in closest to linear search algorithms, that is O into n. In real-time data, we cannot predict data pattern and their frequencies. So, a near left rotation and right rotation is required. The first two rotations are single rotations and the next two rotations are double rotations. To have an unbalanced tree, we at least need a tree of height 2. With this simple tree, let's understand them one by one. First, we'll start and we'll read array A and value x. If n is equals to length of A and beginning is 0 and end is minus 1, n minus 1 and result will be 1. We'll check the condition that if beginning is less than or equal to n, if it is not, we'll come out of the loop. If it is s, middle will be equal to beginning plus n by 2. Again, we'll check the condition called if a of mid is less than or equal to x. If it is s, beginning will be equal to middle plus 1 and the result will be middle. If it is no, end will be middle minus 1. Binary search tree. An internal sort is any data sorting process that takes place entirely within the main memory of a computer. This is possible whenever the data to be sorted is small enough to all be held in the main memory. For sorting larger data sets, it may be necessary to hold only a chunk of data in memory at a time. Since it won't all fit, the rest of data is normally held on some larger but slower medium, like a hard disk. Any reading or writing of data to a form this slower media can slow the sortation process considerably. This issue has implications for different sort algorithms. Common internal solving algorithm. There are two important limitations to pure stack based on storage allocation. First, the only way to return data from a procedure or function is to copy it. If you try to simplify or return a reference to it, the storage for the data will have vanished after the procedure or function returns. This isn't an issue for scalar data. like integers, float, and boolean, but is an issue for large objects such as arrays. For this reason, you can't find an example. For example, return a locally declared array from a function in C. Second, you can't return a procedure or a function as a value or assign a procedure or function to a global variable. Like procedures or functions values are arrayed first class citizens. Our next topic is comparison between linear search and binary search. Binary search requires the input array to be sorted, whereas linear search can work on both sorted and unsorted arrays. Efficiency. Binary search is more efficient than linear search, especially for large data sets. Binary search has a time complexity of O into log n, while linear search has a time complexity of O into n. A linear search, commonly referred as sequential search, simply reads each element one at a time. In this search, an array is symmetrically scanned from its first element to its end, or till a desired element is located. This approach is only applicable for searching over a tiny array or an array that is not sorted. The last part of my topic is conclusion. This paper covered the basis of data structures. With this, we have only scratched the surface. Although we have built a good foundation to move ahead, data structure is not only just limited to stack, queue, and linked list, but it is quite vast area. There are many more data structures which include map, hash tables, graphs, trees, etc. Each data structure has its own advantage and disadvantages and must be used accordingly to the needs of application. A computer science students at least know the basics of data structure along with the operations associated with them. Many high-level and object-oriented programming languages like C++, Java, Python come built in many other these data structures. Therefore, this is important to know how things work under the hood. Dynamic data structures require dynamic storage allocation and reclamation. This may be accomplished by the programmer or may be done implicitly by a high-level language. Thank you for watching my video. If you like my video, please do like, share and subscribe.